Okay, I guess it's time to resume. Welcome to the second and last one of the talks of this afternoon on the joint analysis seminar with Princeton University. The second speaker is Palasek, and he will talk about the Navier-Stokes equations at critical regularity, but I'm guessing it's incompressible Navier-Stokes equations.
Yeah, I probably should have known to clarify today, but okay. Yes. So thank you, Camila, for the introduction and for the invitation, and to all of you for especially those who came all the way from Princeton. So yes, today I'll talk about the incompressible Navier-Stokes. See, I wrote it on the second slide with initial data. So we're interested in the Cauchy problem. The data is assumed to be divergence free. So the most classical result in this direction is due to Loret, who showed that if your initial data is sufficiently regular, so let's say it's C infinity to be extremely generous, then there exists a smooth solution for at least a short amount of time. And I should say that we're working on the torus, so I'm not going to worry too much about decay and things like that. And most of what I'll say is in 2D. Various points I'll make references to other numbers of dimensions. So if you iterate this local existence, then as we all know, you either can do this forever and you get a global solution, or these times of existence stack up and you get a blow up. Now let me widen the perspective on this picture. So let's say our initial data is maybe not quite smooth. Let's say it's in some other space. So the way we categorize spaces of data is based on how they interact with the natural scaling for the Navier-Stokes. So this operation preserves solutions not on the torus, but on let's say the whole space. And so depending on how your space interacts with the scaling, you either are what we call supercritical, subcritical, or critical. So in the supercritical world, this is the worst case. Generally speaking, these problems are ill-posed in multiple ways. So for example, we now know due to works on convex integration by, for example, Buckmaster-Vico, Cheskidov, Luo, and many others, that when you have data in the space, you can have non-unique weak solutions. I just say I'm slightly conflating here the regularity of the data versus the regularity of the solution for positive time, but the story is very similar, no matter how you interpret this. So supercritical is bad. You have non-uniqueness. You have norm inflation. So what this means is you have discontinuity of the data to solution map at 0. So you can have arbitrarily small data that becomes arbitrarily large very, very quickly. On the other hand, the other side of the spectrum would be supercritical data. This is the picture that I gave on the previous slide. So in this setting, we have this local well-posedness, and the big question, of course, is whether this local can be extended to global, which would be something like a blow-up. Now, the sort of Goldilocks question, which is going to be the subject of this talk, is what happens in between at exactly the critical regularity. So examples of data at the critical regularity would be L3, H half, and then VMO -1 is a little more exotic, but an important space in the theory of these equations. So in this setting, the questions are a little more delicate, and there are still things that we would like to know. So that's what I'll talk about. Now, I think for this audience, maybe I don't need to say what this means, but just so we're all on the same page, I'm going to give you 3 meanings of what it means to be critical. So the first one is kind of an algebraic one. It means that when you take the scaling, the norm stays invariant. Another way to think about it is that once you scale out the viscosity, the norm is dimensionless. This is kind of the physics definition. So here, the critical norm maybe has something to do with the Reynolds number, and depending on what type of physical setting you're talking about. And it's nice to talk about a dimensionless norm, because then it makes sense to talk about small data versus large data. The scaling does not affect small versus large. And then another way to think about it, this is the PDE way to think about criticality, is if you're controlled in a critical setting, that has as a consequence that somehow the nonlinear term is very heuristically speaking controlled by the linear term. So in as much as the Navier-Stokes equations are a battle between the smoothing effect of the heat and the amplification from the Laplacian, having some kind of bound in a critical space amounts to saying that there's a limit to how strong the nonlinearity can be relative to Laplacian, and roughly speaking, it means they can be of equal size, which is why it's such a delicate thing, because it's not very clear which one of them should win, and it depends on exactly what question you're talking about. So
Do you want to add translation invariant or not?
yes, let's say translation. Okay, so what's known in the setting? So certainly the most classical results for critical data go back to Fujita-Kato and Kato. So they showed that you can look at the mild solution formulation of Navier-Stokes, and you can design a very special type of space where you can construct solutions using a fixed point argument. And so for small data, you use essentially the fact that the nonlinearity becomes perturbative, and you get global opposedness when your data is below a certain threshold. On the other hand, at the same time, for these particular spaces, H-half and L3, and similar ones, you get local opposedness in general. So this boundedness of the map in the mild formulation of Navier-Stokes, you get a better constant as you take smaller and smaller time. So you can also show short time opposedness even for very large data. Now, if you move to slightly worse critical spaces, specifically critical spaces that include this 1 over x function, which is important because, for example, forward self-similar solutions start to contain the 1 over x function, then the theory changes a lot, and this is a little bit more modern. It was developed in the 90s. So in this tier of critical spaces, you still have, and these are some examples, for example, weak L3. In this category of spaces, you still have global well-posedness when you have small data, just as in this case, but the local well-posedness starts to fail. And the reason is simply because it's no longer the case that when you take time smaller and smaller, the bounds you have on the bilinear operator actually have a constant that goes to 0. So as far as these classical results are concerned, they have nothing to say about large data, even for a short amount of time. So that's a big question that I want to try to address. And then there's one other category of spaces. Here I'm grateful to Igor's question. So if you include the definition in your definition of criticality that you should have translation invariance, you can prove the largest critical space in existence for Navier-Stokes. So if you look at spaces like this one and similar ones, the Navier-Stokes becomes ill-posed even for small data. And this was shown first by Bourgain and Pavlovich, an example I'll talk about a little more later. So the way I think about this picture is these spaces are kind of irredeemable. These spaces are we might as well be smooth. And then this is where most of the interesting questions lie. So more concretely, these are the questions that I'm going to try to answer. So the first one, these are the questions that are outstanding. The first one is whether the local opposedness in the good spaces can be continued forever. And the second one is whether the small data assumption on these borderline spaces is actually necessary. The first one I will not try to answer because it is very hard, but I know there are people out there trying to. The second one, though, we're going to try to address to some extent. So some concrete things one could ask is, do you have uniqueness? That would be a obvious way that you could have a breakdown in local well-posedness from these spaces. And ideally, you would like this uniqueness to be in the same type of class that you would prove well-posedness from small data. Of course, if you just talk about solutions with data in the critical space, but you put no requirement on how they evolve, maybe they become distributions with infinite energy, then of course you can say quite a bit. But let's try to keep it to solutions that stay relatively nice in some kind of critical space after the initial time. The other thing we want to ask about, in terms of the classical notion of well-posedness, is whether you have nice quantitative properties of the data to solution map, and whether you have continuity of the data to solution map, and questions like this. So part one of the talk is going to be about non-uniqueness. So to this date, there have been two, broadly speaking, frameworks for how to prove non-uniqueness of fluid equations. The first one was pioneered by, of course, Camillo in collaboration with Laszlo Zekohidi. So this idea of convex integration goes back to Nash and Gromov for problems in geometry. but it was brought into the theory of fluids. It has been wildly successful for the Euler equations and has resolved a lot of important questions for Euler. For Navier-Stokes, the success has been more mixed, I would say. So for Navier-Stokes, the first construction of non-unique weak solutions was due to Buckmaster and Vikol, who constructed solutions that are basically, you could say, an H epsilon uniformly in time. So when you compare it to, for example, the critical space H1/2 or the energy space, you see it's quite far. Nonetheless, it's a huge breakthrough. This was the first non-uniqueness for Navier-Stokes in general. In terms of the critical regularity, very sharp results were obtained in this work, 2 papers by Cheskidov and Luo, where they got very, very close to certain critical classes of solutions, this proteacerin class. These are sort of the sharpest results from convex integration. But let me say that in terms of the optimal results you would hope for example, you'd like to construct solutions that are smooth for a reasonable number of times, almost all or all times. You'd like to construct solutions that are sharp in terms of regularity and maybe that are in critical spaces. And most of all, you'd like to construct solutions that have finite energy. And the energy for the Navier-Stokes includes both this L2 norm for kinetic energy and also this L2H1 norm for the energy that's being dissipated. For these problems, for these questions, the convex integration approach seems quite far from getting there. So that's one approach. The other approach to non-uniqueness for fluids is what I'll call non-uniqueness by instability. This is a method that was really pioneered by Haujia and Vladimir Sverok. And what they suggest is that if one can find a smooth, unstable solution to the Navier-Stokes equations in self-similar coordinates, so something that's stationary but unstable in this evolution, then there's a way that you can basically use the instability at time minus infinity in self-similar world to construct non-uniqueness at time 0 in physical coordinates. And that would be in certain ways sharp in terms of the regularity. It would look like 1 over x. And if you suitably truncate it, which G and Sverok showed how to do, you would get something with finite energy as well. So some progress has been made on this one. So the first result was with a force by Albrit and Bruy and Colombo using an instability for 2D Euler discovered by Vishik. And then so using a computer, there was an unstable profile found with no force by Guillaume and Sverok. And a computer-assisted proof of the existence of a different numerical profile was recently announced by Tom and Host Group at Caltech. So these are the 2 known ways of constructing non-uniqueness for Navier-Stokes. But one purpose of this talk is to show another that it gets sharp results that are sharp in a somewhat different way, and is somehow doesn't make use of a computer. So let me introduce the idea, but first in the context of a dyadic model. So this is the Obukhov dyadic model for the Navier-Stokes equations. So now instead of considering a PDE, we consider a countable sequence of ODEs that are going to represent the flow of energy through different scales. So here NK is a sequence of frequencies. Maybe you could imagine it is a geometric sequence for now. XK represents the amount of L2 in the energy shell near frequency NK. So XK squared would be the amount of kinetic energy in that shell. And then alpha is a parameter that somehow models the amount of intermittency in the fluid. These models were brought into fluids by Katz and Pavlovich. I should say brought into mathematical fluids. They have been studied by physicists to model turbulence for quite a long time. But it's a nice setting to understand phenomena that then maybe you hope you can learn something and transfer to the actual PDEs. So let me explain a little bit what's happening in the system. So I've labeled the 3 terms. So the first one is easy to see. This is dissipation from the Laplacian. And then these are the 2 nonlinear terms. You have some choice as far as how these are, but in terms of nearest neighbor interactions between adjacent shells, you basically have 2 choices. This is one of the 2. So if you imagine the XKs are positive, this first term is cascading energy from a lower frequency to a higher frequency. So I call it an upward cascade. And then this second term that's negative is sending energy, is basically balancing the energy that was sent up. So it's sending energy back down. So these terms are chosen, first of all, motivated by the PDE, but also they're chosen in such a way that they exactly balance in terms of the energy transfer. So you can verify that this model has energy conservation for regular enough solutions. There's also an Onsager thing where this can be violated by rough solutions. But formally speaking, this conserves energy, which is one reason why this is a good model for the Navier-Stokes. Of course, whether it's a good model depends on exactly what setup you're using. But as you'll see, we can get a lot out of understanding this model. So let me tell you abstractly how you can get a non-uniqueness mechanism from this discrete model. So the basic idea is that in the same way the Navier-Stokes has this continuous translation symmetry, the dyadic model has a discrete translation symmetry, and this is an exact analog. You can check of that symmetry. So the strategy is to find a family of solutions to the dyadic model that are discretely self-similar, but not with every rescaling, not every scaling by the ratio between scales, which is lambda, but only when you rescale by lambda squared. So it's self-similar, but only when you jump across two levels. So that's why we have this equality for the even integers, but when you try something odd, you get different things. This is a type of discrete self-similarity. So the trivial observation, if you find an exact self-similar thing like this, is that if you rescale it by one, you get a distinct solution because of this non-equality. But the data also gets rescaled. So if you can find something in this family such that the data is actually self-similar, but across every jump is self-similar, so it has more symmetry than the solutions for positive time, then you could get non-uniqueness. So the plan, at least morally, is to find a family like this that's somehow rich enough that then you could exhibit member of the family that has more symmetry for the data than for the evolution for positive time. And that would let you finish. This is very, very idealized, even for the dyadic model, because in practice, the self-similarity will not be exact, it will be approximate, and you're going to want to truncate in order to get things that essentially have finite energy and so forth. But this is the strategy. So I won't go into a ton of detail about how this is done because I want to get to the PDE, and what transfers to the PDE is much more the philosophy than all of the details. But the bottom line is that with this mechanism, I was able to get a sharp non-uniqueness for this dyadic model. So let me just explain the notation. This B space is analogous to Besov spaces. So this looks, in terms of regularity, when you unpack the meaning of the model, a lot like a self-similar solution. This parameter alpha, the proof works for alpha bigger than 2, which is the supercritical range. So that's when you expect it should work, and the solutions are smooth. So since we're working on the Fourier side, smooth really means rapidly decaying. So these are solutions that after time 0 are decaying exponentially. They also have constant energy, so they're the Rayhoff. So in many ways, these look like the solutions that come from, for example, the Giash-Farrock picture, the self-similar solutions. But they come from a very, very different mechanism. They come from more of a discrete thing than a continuous symmetry. So here's a little bit more about how this works. So recall that I said that we should have some kind of symmetry only when you jump across 2 levels. So that's what this picture is showing. So maybe you imagine one solution is this left picture. So you have some mechanism, some binary interaction between modes that's happening between 0 and 1, x0 and x1. And then you have something that's the same but scaled happening between 2 and 3, and then so on. And then maybe you have another one that's the same, but now everything is shifted by 1. So this is the kind of picture that one can do up to various errors and things. Let me say a little more about what's happening within the binary system. So this is a phase portrait that shows 2 adjacent modes. On the horizontal, I have, let's say, xk minus 1, and on the vertical, I have xk. So really what I want to take away from this picture is that the goal is to get a trajectory that converges to 0. So the goal is to find something on this stable manifold. The upward flow is coming from this particular upward cascade term in the dyadic model, this leftward travel is driven by this downward cascade term, and then this decreasing at the end is driven by the dissipation. So all three of these terms are necessary for the mechanism, and I want to say just briefly that in order to get finite energy, you really need xk minus 1 to start off bigger than xk, because recall that the energy is given by the sum of xk squared. So if you want finite energy, you need this series xk squared to be summable, so you need the energies to be decreasing. So it's very important you somehow start over here. So all three of these terms are needed. In particular, you need this initial upward motion in order to raise the energy of essentially the higher frequency one is stealing energy from the lower frequency one. So all three of these terms are necessary to achieve this picture. So the question is, can we embed these mechanisms into the PDE? That would be the best case scenario. I have to mention that this is very analogous to a program that was proposed by Tao for the blow-up problem. So in his case, he invented a dyadic model. His dyadic model is extremely complicated, but in spirit, it's the same approach. And he shows that the dyadic model blows up in finite time. And then he asks, does anyone know how to embed this in the PDE? And it seems very, very hard. But I think for various reasons, it's actually easier to do the non-uniqueness program. For one thing, the dyadic model that I'm proposing is much simpler. So this is the Obukov model one more time. Let me explain to you how the terms in this model correspond to interactions in the real Navier-Stokes equations. So the nonlinear terms in the model originate from taking some Boni type decomposition of the nonlinearity, and you throw away most of the interactions. So the ones that you keep are these two. This first one is the upward cascade term, and the second one is the downward cascade term. So you really, if you want to embed this scenario into the PDE, you need to embed both of these types of interactions into the PDE. So the good news is that this term, for any of you who have studied convex integration, you're probably very familiar with this. This high to low cascade is exactly how we build things in convex integration. We use this interaction precisely to cancel an error at, let's say, the NK frequency shell, using interactions at the higher frequency shell. So the bottom line is that this term is very easy to handle if you are familiar with that literature. This term, on the other hand, is much harder to handle, and it's really the obstruction to fully resolving this problem using this method. So just reminding you of this picture, but now replacing the dyadic interactions by the PDE interactions, we know how to get the leftward motion because of this convex integration idea. We know how to get the downward motion because that's just the Laplacian, but the upward part, we really, it seems to be a challenge. So we are able to make some partial progress by partially embedding this dyadic mechanism into the PDE. But what we are forced to do is basically start up here. So not use the upward motion, basically only use this one to move to the left, and then use the dissipation to move downward. So that's going to be the strategy of the theorem that I will state next.
Oh, you have a condition that alpha has to be bigger than 2?
Yes.
This model would suggest alpha equal to 1.
Sorry, which model? What do you mean with this model?
Your statement said alpha is bigger than 2.
Yes.
And this dyadic model.
Are you saying this because the nonlinearity has one derivative in it? Yes. So I should have been more explicit about this. Yes, it's because xk represents the L2 norm. So there's a mismatch between L infinity and L2. Yeah. So yeah, maybe let me make this explicit. So in the Kolmogorov picture where the turbulence is homogeneous, there's no difference between L infinity and L2. So the alpha would be 1. But in the intermittent picture, for example, for a self-similar solution, there's a huge difference between L infinity and L2 from Bernstein inequality, and you saturate Bernstein inequality, so actually alpha would be 5/2. So really the meaningful range is between 1 and 5/2 if you're in 3D. That's a good point. Okay, so this is the theorem that we're able to prove using this dyadic inspiration. So the setup is that we work in the space PMO minus 1. I won't explain the definition in detail, but let me just say that this is an extremely natural thing to write down. and it happens to be a critical norm, and it happens to be a brand of initial data for which you can prove global regularity when this norm is small. But I can say more about why it's natural later. So the famous theorem of Mutaru is precisely what I said. If you're small, then you have a unique global solution. So the way they do this theorem is they concoct some space xt, which is, you can almost already see how you would define the space xt, because basically the heat flow becomes the solution, and this is then what you're left with is pretty much essentially the norm that gives you this path space. That corresponds naturally to this type of data. So they show that this operator gives you a contraction on a sufficiently small ball in this net. So the question naturally arises, what happens when you have large data? So this is the theorem. It's joint with Matei Coiculescu, who's a student at Princeton. I don't think he's here today. So the theorem is that we can exhibit an initial data in the space that gives you two global solutions that are distinct. So they're smooth for positive time. We have enough continuity at time zero to confidently tell you that this is meaningfully a solution. They are in the same path space where you get the global regularity when you're small. The data is also smooth on everywhere except for some measure zero exceptional set. Unfortunately, it's not L2. The reason it's not L2 is because of that phase portrait I showed you, the fact that we could not get this upward part to work. So we really have to, unfortunately, take the data at the higher frequencies to have more energy than the lower ones. So that's why it's not L2. And the other thing that's interesting is that in some senses, this is very sharp. So for example, I mentioned earlier, there's this famous Prodi-Sarin scale. This is a scale of space-time norms that are critical. And we know that if I give you weak solutions that are in any of these spaces, then it's automatically a strong solution, and its solutions are unique and so forth. So if this was L2, L infinity, it would be impossible because that's on the scale of regularity criteria. So these solutions are in weak L2, L infinity. They're also, for example, you can weaken it like this. So you can, instead of having L2 in time, you can make it this Orlich type norm with as many. And we proved it with maybe 1 or 2 logs, but in principle, you could easily modify it to get as many logs as you like. So this really shows this Prodi-Sarin space is very, 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 very sharp. Yes.
So the first comment, when you say that the solutions are in the Banach space where Koch-Taro run the fixed point argument.
Yes.
That includes the space-time norm.
Yes, the XKT or the XT, whatever. But large, of course, a large.
Right, but it's not just the norm of initial data that you're looking at. It's
correct.
Also the smoothing norm as well.
Correct. Yes. It's worth mentioning that if you want to experiment this with critical data, but you don't care about the regularity for positive time, there are theorems that let you do things that are impossible in this regime. So for example, if all you care about is the solution being in L2 at every positive time, maybe L2 decreasing, then you can do this for smooth data. So this somehow only tells you something about this mild solution picture when you have some reasonable regularity after the initial time. Okay, so let me tell you a bit about the proof of this result. So the data very much, as you'd expect from the model, is constructed as a series of lacunary, I give you some lacunary sequence of scales, and the data is going to be something that we construct somewhat explicitly localized in each of these frequency bands. So the big claim that will make this mechanism work is that you can choose the data such that from every frequency localized piece of the data, not the full data, but just each localized part, there are 2 consistent ways that you could have the evolution unfold. Way number 1 is the trivial one. So since I give you something frequency localized, it can evolve according to the heat equation. And in that case, basically the L infinity norm is just going to decay in an exponential rate on the time scale given by the frequency. So this is, we call the heat dominated flow, and we write VK with no bar. Okay. The other way that it could unfold with the same data, but somehow with a different flavor of evolution, is what I call the inverse cascade dominated flow. So this I denote by VK bar. And here, there's no Laplacian. The Laplacian will be negligible. Instead, it's being driven by a force that's coming from the shell above it. Okay, so this is why it's inverse cascade dominated, because this is an inverse cascade. It's energy that's being sent down from the mode immediately above. So it has the same data, but it has a different way of unfolding. And I want to emphasize that this VK plus 1, this is the non-bar V. So this is the V that is being essentially evolving by the heat equation up to low order terms. Now, the big claim is that you can arrange the data such that when this VK bar evolves, according to this, the L infinity norm is much, much faster than what would be allowed from the heat equation alone. So the normally VK bar would want to evolve like, e to the minus nk squared times t. Here it's evolving like nk plus 1 squared. So it's much, much, much faster. So somehow this is happening on a time scale that's way too short for the heat to have any impact. So the claim, and this is, of course, a lot of the proof is to show that you can do this, is that you can construct data that's localized such that both these things are the case. Now, here's, okay, yeah, and moreover, that those are the only interactions that are non-perturbative. All the other many bony type interactions are going to be negligible, as well as, the Laplacian hitting other things. Everything else we will show is an error. So once we have these two ways of evolving from each frequency localized piece, the way we construct the actual solutions is by putting them together in an alternating way. So one solution will come from basically putting the non-bar ones on the evens and the bar ones on the odd, or vice versa would be the other solution. So you can kind of see the parallel with what happened with the dyadic model. So the distinctness will be clear. Like I said, the VK and the VK bar have completely different rates of decay. But let me explain heuristically what's happening for this non-uniqueness. So what's going on is that if you fix one piece of the data, let's say the VK plus 1, 0, because of the definition of the bar parts, it's capable of using its nonlinear interaction with itself to completely annihilate the part of the data at the next lower frequency shelf. And that annihilation occurs on a very, very fast time scale, and on this time scale. Similarly, the VK0, because the situation is totally scale invariant, it's also capable of annihilating the mode that is immediately below that one, but it happens on a much longer time scale, VK to the minus 2. These two events are not compatible because if the VK plus 1 annihilates the VK on this very short time scale, the VK does not have enough time to act on the one below it. And therefore the VK is left. And it can then act on the one below it and so forth. So that's how you get this kind of symmetry breaking in the scaling sense. So and because of this incompatibility, the only way you can set this up to be consistent is to do this alternating picture. So that's the kind of heuristic philosophy behind the construction. So let me tell you a little bit about how we construct these things, and I'll leave out some of the details. Not as exciting, but here's the main idea. So as an initial cartoon picture, let me imagine that the localized part of the data looks like a coefficient times a rapidly oscillating function, and that the rapidly oscillating function is a shear flow. So the eta and the theta are perpendicular. And moreover, the A lives at frequencies that are much smaller than the N. So because the A lives at much smaller frequencies from the N up to a small error, the heat flow will only impact the sign, the oscillating part, and so basically the heat-dominated flow should look like this, up to small errors. So this is the trickier part. So recall we want to achieve inequality like this. So if I take the VK and I plug it into the thing that we desire, this equation, you get something like this. Now, the really nice thing, and the thing that for people who are familiar with convex integration is a huge distinction from that method, is that here the A is not actually a function of time. The A is only affecting the data. The A is only a function of space. So the only dependence on time in this equation is through this exponential. So this basically is an ODE. This basically is an ODE. So we can integrate both sides in time, and you get this trivial integration. And recall our desire was to make the V bar decay on a very, very fast time scale. So this part is not decaying. This part is not decaying. This part is, of course, decaying. So you can achieve this precisely if you make this term identically equal to this term. And so you're led to this equality, which you want to very precisely set, up to all kinds of errors. So the idea is going to be you build VK0 and then you want to choose AK plus 1 in order to achieve this. So you can see that this is maybe not possible as I wrote it, because this right-hand side is going to point more or less in the direction of theta, ignoring the Leray projector. And so unless VK always points in the direction of theta, this is not true. But at this point, we borrow another idea from convex integration, which really goes back to Nash, which is that what if instead of having only one direction theta, we allow ourselves as many as we need to have a much richer set of directions in which we can add these perturbations. So instead of having this single oscillating piece, we have a sum of pieces that are oscillating in different directions. Now you have to arrange these things carefully in such a way that they don't interact too much with each other and create other adverse errors. But I mean, once you can do this, I'll show you that it is possible to attain this equality. So if you write this piece of the data as a basically a Laplacian of some potential, this makes it divergence free, but it also makes it in the form of the divergence of some symmetric tensor. So when you use Nash's idea, what you realize is that you can decompose any positive definite symmetric tensors in terms of a sum of these rank 1 tensors. So if you want to solve this equation, where I've now replaced our data by the same data, but now in this form with the potential, you see that we basically want to make an equality between this piece and the d psi. And this is now doable. Using this Nash lemma, you can prescribe the coefficients in such a way that I should really have a sum over I on the right-hand side, but this lets you prescribe the coefficients. So when you do this you've defined A's, and now you have a recursive equation that relates basically the size of the A to the size of the V, and therefore the size of the next V. And it looks something like this. And this is good because this is critical. This is exactly the critical regularity, because the right size of the velocity should basically be the same as frequency for Navier-Stokes. So when you rearrange this, you get this relationship. And then when you solve this recursive relationship, you get this. And as you take k to be larger and larger, this factor is going to 1. And you find that the size of the data is just going to nk, which this is the size that gives you at least the worst Besov space. Okay, you need to upgrade it a little bit, but this at least puts you in the critical regularity. Just two small observations. Because of this repeated square root, we don't lose constants, which would be a serious danger in convex integration, for example. So that allows us to truly lie exactly in the space. The other observation is that this is why we can't produce data. If you tried to start this iteration with a small v00, then this square rooting would make it big, right? So that should be reassuring. If we could make small data, then that would contradict the Coiculescu theorem. So this is reassuring. So I'll talk a little bit about how we correct the errors. So at this point, I've described a recipe more or less for how to construct approximate solutions that have a force on the right-hand side. So we have two solutions that have the same data. So the goal is going to be to, of course, correct the error. So we need to show something to the effect that this force is small. Now, if you write out all the terms in this force, eventually you can estimate all of them. They're all good in some way. So they're either good in the sense that the size is subcritical, in the sense that the critical would be n squared in terms of the amplitude. So maybe they're subcritical in the sense that it's like nk minus 1 times nk, or they're subcritical in the sense that the time decay is better than critical. They decay much faster than the natural parabolic decay rate. So in either case, we get good estimates. You get smallness, but even better, you get subcriticality. So what you actually find is that the force is not just small, but it's subcritical, and that becomes very important in the proof. You define a space that's going to contain the force and also the nonlinear interactions that's a little bit subcritical. So by taking this alpha positive as opposed to 0, this is a little bit subcritical, and we show the force is small. So we've produced a solution to this. We would like to correct it. So we do that by constructing another field called W. And as you can see, if W is made to solve this and V is made to solve this, then the sum of V plus W will exactly be a solution of the Navier-Stokes, right? So by constructing a W, you'll get a full solution. And one hopes that because the force is small, you can do this. And moreover, the W will also be small. Let me point out that since the V's had the same initial data, we want the W's to have the same, to have zero initial data. That way, when we add them, we get something with the same data. So the linear terms make this hard. This is the same obstruction that you run into in lots of problems in PDE where you have some exact object and you want to correct it. And as long as it's perturbative, often the nonlinear part is not such a big problem. But the linear part becomes very harmful because the V lies in a very degenerate space, especially near the initial time. So you need to somehow tame these linear terms. So the way we do this is we try to understand the semi-group that's coming from the linear part of this equation for W. And then, if we can get good enough estimates, then we can construct W as a fixed point of an operator like this, using the fact that F is small, and then if W is small, the quadratic interaction is good. Now the semi-group is bad because the V is right at the critical regularity, unfortunately. But the good news is because W has zero initial data, we don't actually need to propagate anything from times W. You only need to do this for positive time. So it's good enough to get estimates for W for positive times. Of course, these are going to deteriorate as you get close to the initial time. And they do deteriorate worse than the heat equation. So these are the estimates that we prove for this semi-group. This little t over t prime to the epsilon shows you this. You can make it a little bit worse than the heat equation, for example, would be. I'm not going to go too much into the proof. All I want to say is that the reason we can make the deterioration as mild as we like is basically because somehow it has to do with the number of concentrations of the solution in time as we get very close to the initial time. And because we can make the components of the solution very, very lapinary, the times on which they're active can be very, very spread out. So that's why really the bad contribution to the semi-group, we can make it as mild as we like. So that's how we can get epsilon, or we could even do better if we had to. So yeah, we make the separation between the NK large is the trick. So this allows us to solve a fixed point problem, and from here it's pretty standard. So I'll skip the rest of the details. The real moral here is that the subcriticality of our estimates on the force are enough to defeat the little bit of loss we get from the semi-group. Yes.
So should I think of it as, okay, so for this space, you don't have uniqueness, you have non-uniqueness.
You mean the space, this X?
Or the space in which your solution lives.
Oh, yeah. Oh, yes, okay.
But you do have propagation of regularity.
In the BMO-1, the Coiculescu path space, we do. Even the Coiculescu path space, there's propagation of for small.
Now
for large.
For large solution.
Yeah, for large.
Is that basically the interpretation of this?
No, I see. Sorry, now I understand. No, actually, we do not have propagation for large data in B1-1. That's part of the talk, yes. Or at least not quantitative.
It almost says that, because it says that if the right-hand side is slightly better, you can actually propagate. You can put the correction in a better space.
Yeah, but the right-hand side has to be better in a way where you gain a whole power. So that's significantly.
What does it mean, the whole power?
Or in the sense that the force is better. The force is better by. It's not just small. I mean, the force is small in the with the power saving.
So better regularity. So if you put your data at the right-hand side in a space which is strictly better regularity than the space where your solution is, which is in the critical space, then that's going to be propagated.
I see. Yes. Not for a generic BMO-1 or Coiculescu or large solution in this class, because in our solution, yes. It's really the lacunarity of the scales that helps you a lot. Yeah. So yeah, maybe this is worth emphasizing. If you had a self-similar solution, there would be no lacunarity in the scales, and you would not have this. Yeah. So there are senses that I mentioned that actually our solutions are better than the self-similar solutions because you can make them as spread out as you like. Yeah, that's a good point. Yes, for generic solutions, this would not work. Generic backgrounds. Okay. Yeah, so that's the construction. So at this point, it's just a standard fixed point. Now we have these estimates. So So the first part of the talk was about non-uniqueness. What was propagating down through frequency scales was not energy per se. It was really, I would say, sort of influence in the sense that there was some influence that was happening at high modes that was cascading. But another thing that you can do is you can start to actually try to propagate energy down and start with something that's only big at a very high frequency and then conducts a turbulent cascade that will cause growth at lower frequencies. So, the motivation for this problem is the question of a priori estimates for Navier-Stokes. So one can reasonably ask, do you have bounds like this for some space X, where you're measuring the data in some space, and let's say F is allowed to be any increasing positive function? Or do you have bounds like this that are of a more parabolic smoothing type in terms of the data measured in some space? So the motivation is really, if you'd like to understand the global regularity question, you would really like to recast it in some kind of quantitative form where it boils down to proving an estimate instead of proving something just to the effect that all solutions become, stay singular, but could potentially become arbitrarily large on the way. So this is really the enemy in some sense is that, the solutions can become arbitrarily large and then by some non-quantitative mechanism always smooth themselves out. So this was a question asked by Tao. He showed that this cannot happen when the space you measure in is H1. And he asks what happens when X is critical. So when X is a good critical space of the type I mentioned early on, like L3, it was shown that the same is true. So in fact, you cannot have you do not have regularity for Navier-Stokes without also having a priori bounds on the solutions. Or equivalently, if you disprove a priori bounds, then you've proven that there's a blowup. So this is essentially a compactness, showing that if you have a sequence of solutions that's getting worse and worse and worse, despite the data being bounded, then by compactness, you could construct an actual blowup. Now, what happens in worse spaces is the question. So as I mentioned earlier, if you're in a very, very, very bad space, these norm inflation results, whether it's a bad critical space or even a supercritical space, will disprove this type of claim that norm inflation is equivalent to blowup. Borderline spaces are once again the delicate question. There's evidence that when you take one of these, for example, weak L3, there is still a notion of solution for Navier-Stokes that's a little bit more delicate that gives you enough compactness to still show that the global regularity is equivalent to a priori bounds. The remaining space that is not covered by these is BMO -1. So something that I showed is that for BMO -1 data, you can have a family of initial data that's bounded, but can violate essentially any a priori estimates. So maybe that's too general to say essentially any, certainly the types I listed on the last slide. But this gives you an idea of how broadly you can violate a priori estimates. So I state this one in a slightly better space than BMO -1, but if you prefer, you can think of it as BMO -1. So there exists a family of data that's all smooth, but you can arrange it in such a way that it stays bounded, but yields a solution that becomes arbitrarily large in the scale invariant sense. So this theta star is a parameter that you can choose arbitrarily, and this error is something that you can make arbitrarily small in a very high regularity norm. And the solution eventually starts to approximate this very large exact solution of Navier-Stokes on some time scale. So as a result, clearly, this is getting large in any critical space and almost anything you could think of become unbounded. So let me describe a little bit about the growth mechanism. So I want to contrast it with the one of Borgen and Pavlovich that works for small data in this very, very bad Besov space. So the way their mechanism works is you start with a very, very large number of components of your initial data at different frequencies. And each one is allowed to be small, but it contributes something even smaller to the part of the solution that lives at low frequencies. So I should say that the vertical, of course, is the frequency, with the horizontal being the time. So each of these components contributes something, and the more components you take, the larger the solution at the low frequencies grows to be. This does not work in a high regularity norm like BMO -1. Each of these contributions would start to contribute to the BMO -1 norm, and it would no longer be bounded with this setup. So the way this theorem is proven is instead by starting with only a concentration at a very high frequency, and then letting it cascade down to more and more and more. So since you only have one frequency, it doesn't contribute based on the multiplicity to the norm of the initial data. Instead, the largeness is coming from the cascade itself. So this is just a slightly heuristic picture to give you an idea. So if you imagine that the part of the solution that lives at a given frequency is coming from a perturbation that's arriving from the next higher frequency, and I forgot, should be squared. The contribution is something like the square of what was above. And it's the squaring that gives you the growth. So basically every time you cascade down, in a scale invariant sense, the solution gets squared, and then the number of jumps you make can be used to make the solution large. So a little bit more precisely, if you let the CK be the size, the amplitude in the same scale invariant sense of the solution, then this heuristic leads you to this, very similar to the non-uniqueness relation that we had earlier. And if you solve it, you get this. So you can see that by taking the K to be very, very large, this gets completely damped out. So you can take the C0 to be large, which is the size that the solution becomes later on, while still keeping the C's for large K to be small. So in this case, the largeness is really coming from the squaring repeatedly. So by taking K star to be as large as you like, you can arrange that the solution grows to any arbitrary size. Now the next logical thing you can do is imagine, well, what if instead of doing it like this, I let the largest frequency go off to infinity? So instead of having just a finite number of steps where the data is initially concentrated at this one frequency, what if I try to make a cascade that goes all the way to frequency infinity? So in this case, you wouldn't need any initial data, because somehow the energy, this part of the solution is coming from frequency infinity. It never has to have an origin at the initial time. So that's the motivation for the next theorem. So this is joint work with Alexei Cheskidov and Mimi Dai. So we're able to use this cascading mechanism that I described to show the following. So if I give you any initial data that's smooth, could be probably a little bit less regular too, then you can construct a weak solution which is smooth for positive time, continuous in this natural critical topology, while obeying type 1 estimates that still blows up in the same way. So I forgot to write the lower bound here as well, but this inequality is saturated at a sequence of times. So the L infinity norm of U is essentially attains 1 over the square root of t along a sequence of times approaching the initial time. The solution also remains bounded in a critical norm. That this norm is, as you can see, a little bit better than BMO minus 1, because it's saying you're the derivative of an L infinity function instead of the derivative of a BMO function. So it's a little bit better. The other consequence of this is that there's a strong breakdown of uniqueness from any smooth data. So because if I give you smooth data, there exists a local solution, this tells you that there's a very violent contradiction of weak strong uniqueness, right? And not only is there one, but because you can sort of choose where you start this cascade, there's actually a weak star continuous family of initial data that is achieving this non-uniqueness. So unlike the result I showed earlier, this is an infinite family. The other one produces just a finite one. So this is a little bit what it looks like in a picture in terms of the L infinity norm. So you could imagine you have a global solution or a smooth solution that's happily being smooth. And then all of a sudden, at a time we prescribe, you have an anomalous burst of energy come in from high frequencies and cause it to become instantaneously infinite. But the funny thing is that the L infinity norm is actually finite for all t. It just becomes unbounded from the right as you approach this t star. And the one other thing I'll emphasize, similar to the non-uniqueness, is we come very, very close to saturating various classical criterion. So for example, this is a variant of the famous Kato-Maeda criterion. So if you don't have a denominator here, then this is of course a very well-known regularity criterion for Euler Navier-Stokes. So when if you allow it to be relaxed logarithmically, it is no longer a criterion. So you can show that the solutions we construct can be made to have this quantity be finite. Okay, so I think that's all I'll say. I'm out of time. So thank you. There's a picture, and okay, yeah, thank you very much.
May I ask a simple question? Did you consider, under the same assumption of your velocity field, what will happen with a passive scalar or turbulent mixing? That's something which is passively advected without feedback to the flow. Advected and diffused. So there are both experimental data and some heuristic theories, and I have my own. I'm not talking about my own theory. I'm asking what can be proven under the same assumption of velocity about this passive scalar.
Yeah, it's a good question. I think if you're passive scalar, if you could prescribe it to be something that was at this exact critical regularity, I think you could probably achieve something similar.
It would be very interesting, for example, if you prove or disprove regularity of passive scalar. Because in my solution, I don't sell it, but I mean, not for you, for physicists maybe. But the point is that in my solution, there is irregularity of average flow of passive scalar for this ensemble of turbulence ensemble, which I found for the velocity. So it is more singular than velocity. That's why I'm asking.
I see. Yeah. I think. Oh, but you want to be more singular than the velocity, or you want the passive scalar to be more singular than.
Yes.
That might be trickier. I'd have to think about it. Though. It's a good question. Actually, it connects to something interesting. I mean, so that someone just made me order this paper of Lorenz attractor fame, where he asks something very similar. If you, at least to me, it's similar. If you have a like a fully developed turbulence, and then you want to put something on top of it, and he essentially asks a very similar question: can you have non-uniqueness in the form of having a high frequency thing that out of nowhere creates, butterfly type effect, and he does he studies a model equation and essentially shows it, and in that case it would be very similar in the sense that the nonlinear interactions would not be with the perturbation in itself because it would be small. In his picture, it would be with the nonlinear. It would be with the perturbation and the background field. So yeah, I think it's something I want to look into.
That'll be very interesting. If you have any further ideas or positive or negative results, contact me. I would very much.
Good direction.
What happens to the other spaces in Protostep in
the non-L infinity in space? Yes, we don't have enough spatial intermittency to get close. Yes. So it would be very hard because the thing about our mechanism is that, like in convex integration, you basically need the higher frequency thing to cover the low frequency thing. So it really has to have as much support in space as the low frequency thing. So whereas to get saturation of other LP norms at the critical level, it gets smaller. So that's why self-similarity for those is the only game in town. We get a little bit of intermittency for a different reason, but not enough nearly. For the same reason, like the Besov spaces, the critical negative regularity Besov spaces.
Are there any other questions? Well, if not, thanks.